Good morning, good afternoon, everyone. I'm Adam Brown from the University of Zurich, and I think I'm the first of 4 people today talking about single-phase TPCs. And single phase, I mean liquid, and specifically liquid xenon. By way of introduction, there we go. I guess I don't need to convince anyone here about the fact that the dual-phase liquid xenon TPC has been an incredibly useful tool in the last years, particularly in the dark matter community. And kind of works with the S2 signal seen by extracting electrons into gas, where you get a couple of orders of magnitude multiplication from electrons into photons. And these technologies work very well. It's provided some very sensitive detectors. But anyone who's been involved in building a TPC knows it can be quite difficult. And in particular, one of the challenges is that you need this very large, thin gap between 2 electrodes at the top, where your gas gap is to produce the amplification. So you need kind of, now for the newest experiments, meter-sized electrodes a few millimeters apart with a very high electric field. And your electric field will tend to make the electrodes want to sag a bit because of the force on them. And you need to somehow engineer your electrodes to avoid this being a problem, but without using so much material that you block light or even pollute your target of a very clean experiment. And one solution to this might be to get rid of the gas gap completely. And this is what I mean by the single phase TPC. And so with a similar principle, you can produce your S2 scintillation light not in the gas xenon, but in the liquid itself. And this just needs a much higher field. And by high field, I mean kind of several hundreds of kilovolts per centimeter, compared to the, say, 10 kilovolts per centimeter used in the gas. On the other hand, it only has to happen over a very short distance. So it happens in the very close vicinity of thin wires on the anode. So in this context of this talk, I'm talking about 10 micron wires, and the scintillation happens very, very close to the wire itself. And the principle was demonstrated several years ago, in fact, so I put a reference here. And in this plot, you see already the data from that publication. Some threshold, as you go to higher and higher anode voltages, you see larger and larger S2 signals, larger and larger signals. And this kind of proof of principle was done just with an alpha source and a single wire to provide the multiplication. So the alpha source provides a source of electrons. They get attracted towards the wire and very close to this thin 10 micron wire. And if you look at the publication, there's a couple of different diameters used. You get the light produced. Okay, so why would you want to do that? So I kind of already gave the motivation earlier that you can solve some of the engineering challenges that are intrinsic in a dual phase TPC. So because you only care about the local field around the anode wires, you don't necessarily need to have a large scale linear field between 2 electrodes anymore. And you can avoid having the large force on your electrodes that makes them sag. And by the same token, you actually don't care as much if you have some sagging because it's the local field that matters. So this is already a good start. And finally, you can also get some kind of variant designs. So instead of the standard vertical drifting electrons that then get to the top and you produce your S2 at the top, you could consider something like a central wire that runs vertically down the axis of your cylindrical TPC. So you see something like that in the top right here. And there's a couple of talks on this topic in half an hour. And after the next but one talk, and after that. You can also do other things. You could maybe split your TPC into 2, so kind of 2 back-to-back drift regions. And I'm sure there are many other kind of variant designs that you open up that can solve more challenges building these large detectors. On the other hand, the standard configuration that we all know and love still works fine. So you can still have your vertical TPC where you drift the electrons to the top and produce your S2 on an anode at the top of your detector. Okay, and then also, because of the different production mechanism of the light, you get a different type of signal. So we'll see that a bit later. And this can open up potentially some new analysis techniques. And so the very next talk by Fabian will talk a little bit about the possibilities that you can open up just by changing the S2 production mechanism. Today I'm going to talk about our specific TPC in Freiburg University that you see here. So it will look very familiar to those of you who have a dual phase TPC in your lab, or indeed those with a single phase TPC. And it's a cylindrical drift region, 7 by 7 centimeters, with a 3-inch PMT at the bottom, 7 1-inch PMTs at the top. And the important bit for now is the electrodes where we produce the S2. So we have these 3 electrodes, each of them separated by 5 millimeters. So a gate at the bottom, a screen at the top, which are both hexagonal meshes, fairly standard. And in the middle is our anode, that is the interesting one. And so you see a picture of our anode as used for the data that we collected in the spring of this year on this slide. And we're using 10 micron wires, which are tungsten plated with gold. And in this case, they're separated by 5 millimeters. So each wire is spaced by 5 millimeters from the next. And as I said, we tested this anode in the spring of this year, and we were very happy that we saw some S2s. So you see the plot in the bottom right will look familiar to a lot of people, with 2 S1s and the S2 from a Krypton 83M event. And we were very happy to see anything at all. On the other hand, we found it quite difficult to find a stable operating potential. So we had to have a kind of slightly strange configuration where the screen and the gate were on quite different potentials with a very asymmetrical field. And we were very limited in how high we could ramp up the anode itself, which meant that we could only achieve relatively small S2s like you see here. On the other hand, we were able to use the TPC kind of as a normal TPC, do the normal kind of things. So you see here a kind of familiar electron lifetime plot on the left, the S2 getting smaller if the electrons have drifted further through the detector, and some of them have got lost on the way. And on the right, you see something maybe interesting is how the width of the S2 depends on depth. And so our S2s from this single phase detector are actually rather narrow, and basically 200 nanoseconds kind of intrinsic width before you start to have diffusion effects. So the S2s coming from the very top are really much smaller than a microsecond in width. And as expected, if you increase the anode potential, the S2 gets larger. So in these plots, these 2 plots at the top show that they're basically the same fields between all the electrodes, but with a 1 kilovolt overall shift. So that should be the same behavior, and indeed that's what you see. And as the potential increases, the S2 gets larger. In this case, it's fit with a linear fit that seems to fit from the kind of model that is given in the paper that I referenced here, the same one I talked about earlier. You might expect a slightly larger than linear growth. Probably that's what you would see if you go to higher voltages. And this voltage here, so it's again this slightly strange configuration with asymmetrical screen and gate potentials. And what we also saw in our spring data, which at first sight is something not nice, is that we have these 2 different behaviors. So you see an example of the fit that's used to make one of these points. So for 1 voltage in the bottom left. And depending on where in the detector the event happens, we seem to have two different S2 gains. This could be something like a defect on one wire, maybe a slightly different diameter or a piece of dirt or a bad wire tensioning. But what is nice is that it shows us that the position reconstruction still works in our detector. So we can localize that place where there's a higher S2 gain and really see where the events come from, and demonstrates that this works just like it would in a normal, if you like, dual phase TPC. Okay, and so in the last couple of minutes of my talk, I want to talk about something much more recent. So in the last couple of weeks, we've been taking data with a setup that we've been improving since the spring. And you see a rendering of a new anode on the bottom right. So we've got rid of all of the sharp corners that we were worried might be causing some kind of electrical discharge that stopped us from ramping the anode up to a higher voltage. And we also took much more care to keep everything clean while we were reassembling our detector. And with this new anode, then we've been, for the last couple of weeks, taking data, so it's running as I speak, and we've managed to get to much higher voltages, kind of 5 kilovolts anode voltage above the gate and screen. And with that, we've then been able to see much nicer S2s. So you see the difference immediately in this plot, which was taken last week. Again, a krypton event, so you have the two S1s, and now the S2 is much, much larger than before. And what's also nice to see here is what possibly is a hint of an electron, a single electron train after the S2. So you see these small peaks occurring in the time after the S2, and I've blown them up above for you to look at. So each of them consists of a couple of photoelectrons within a kind of 200 nanosecond window. So it seems that we're able to not only see large scale S2s, but also even single electrons, which got us very excited. And that brings me to the end. So to summarize, we've been testing this new technology of a single phase TPC that can relieve some of the challenges, especially building larger TPCs. And it seems that we're going to be able to achieve S2 gains that are comparable to the dual phase TPCs. We've got some very promising results coming out of the detector as I'm talking. And so it would be nice if you keep yourself tuned to hear from us in the next coming months. Thank you.
Thank you, Adam, for this nice talk. There are a couple of minutes for questions.
I would like to ask a question. Did you see any effect of impurities on stability of operation of your system? I mean, if you can apply more stable voltage and see more stable multiplication if you operate in the poor purity xenon, or vice versa.
So this is our assumption, right? We certainly observed that now in our new setup, or a more clean setup, that we are able to achieve higher voltages, and it makes sense. So after doing the run in the spring, we had a look at our anode under a microscope and saw that there's quite some dust on it and particles kind of sticking to the wires on the micron to several micron scale. So it's easy for me to believe that this is what was preventing us from going to a higher voltage.
Yeah, I mean, if you try to purify xenon, you eventually will reach a regime when you will be very difficult to sustain a stable.
Okay, yeah, I see. Okay,
Yeah.
I guess I misunderstood what you meant by purity. With our setup, I guess we don't manage to achieve this regime that you might consider whether it's then detrimental. So it's kind of a small lab TPC with limited purity. We do have a getter, but we're never going to achieve purity like you have in LZ or Xenon.
Okay, we have other two questions. Please let me remind you to raise your hand in case you have questions. Next is Leah.
Hi, I was wondering if you have already results about the S2 energy resolution, because events arriving from different aspects of the wire will have different shadowing, and this should have an impact.
Yeah, so it's not something we have looked at yet. I mean, I put this one plot already here. You see this. You can kind of get a feeling that the S2 energy resolution is not amazing from our spring data. With the larger S2s that we see now, we still haven't done the analysis, is all I can say from data. The shielding effect, yeah, in principle, it's correct, but we don't have any data on it. I guess maybe Fabian will talk about it in the next talk.
Okay, we have time just for one question. Ivan?
Hi, Adam. Thanks for the nice talk. I was wondering if you could comment a little bit more about the sparking and discharging that you saw before, and if that went away with this new run that you're doing now.
Yeah, so what we observed is basically, first of all, that we, at some point, the anode tripped. So we get kind of macroscopic current flowing through it. And we see kind of continuous photon level light being emitted Also, I mean, continuous, but with spikes. Now we're able to reach much higher voltages before seeing any kind of photon level light. At some point you still see it, and without the anode tripping. So our assumption is that this is really some kind of discharge or light production very close to the anode from electrons created in the high field somehow, especially if it had some kind of particles on it.
Okay, thank you. I think we have to stop now. Thank you again, Adam. Next speaker is Fabian Kuger, prospect of S2 analysis, single phase liquid xenon TPCs. Please, Fabian.
Yes, I hope you can hear me, and by now should be able to see the screen, I hope.
Yes, so everything is fine. Go ahead.
Great. Thanks, and hello, and thanks to Adam to bring us these interesting experimental results. I want to talk briefly about transferring this from a small experimental TPC in the lab to large future experiments, and what this could mean in terms of new ways for S2 analysis. Adam talked very briefly already about the theory that's behind this from this first observation in 2014. And I want to make one key statement. Basically, one nice feature about this measurement was that not only light has been measured, but as well they measured the charge directly. So what you see is that besides having an electroluminescence, you as well have an ionization process, which happens at fields starting around 700 kilovolt per centimeter, according to these data. What we see similarly is that our S2 resolution starts to degrade once we get into the range of very large signals, and these very large signals correspond here directly to the charge multiplication. So whatever application we aim for must make sure that our charge amplification is limited to the very narrow part close to the wire where self-shadowing and so plays a larger role. The arbitrarily set limit is what we put for this study is basically a factor of 2, which corresponds here to the onset of the degradation of S2 resolution. Starting from this, we were thinking about how to transfer this concept of electroluminescence in liquid xenon to large size detectors like Darwin or a generation 3 liquid xenon detector. And the idea is to run with minimal design modifications. We do want to maintain the successful detection principle analysis scheme of these experiments. And therefore, the only things you need to do is use thinner anodes, fill up with liquid, and apply high voltage, where of course the last one is the most critical, we know. An example of this is basically shown here, where you see the electron clouds coming in, being funneled through these hex meshes, and then arriving at the anodes, and picking up on Leo's question, by an intelligent design here, an intelligent alignment of those gates, you can avoid having your approaching angles from the bottom, where you have a higher shadowing, but can kind of steer them as you like, because your electrons will always be funneled to the centers of these grids. So what we can look at is what would be potential configurations. We know that if you want a comparable with dual phase detectors, we need a scintillation yield, so an amplification factor of 1 electron to X photons of 100 to 200. And if following the paradigm I set up in the slide before, which is a charge multiplication limit, this would, for example, be possible with an order of 10 micrometer wire at 5 kV. That's exactly what we realized in the Xebra TPC in Freiburg. Or if we want to aim for a 200 scintillation yield, we're more talking about a 50 micrometer wire and order of 15 kV, which of course is much more challenging in such an XY setup. So that's what we assume throughout the study from now on. And I want to talk very quickly through the waveform simulation we applied, which is straightforward. You need a certain amount of electrons. They arrive at your anode with a certain timing. There they produce a certain amount of photons. And then for each photon which you detect in the end, you have a certain PMT response. I will not go through all the details. They are mainly listed for completeness. Let's say for reference, if somebody want to look it up or discuss later, just highlight a few things to show the level of detail we're discussing. So I showed you already this picture of the electrode stack. And indeed, that is what is simulated in all detail. So we assume uniform drift throughout TPC, but for the timing difference, depending on whether your electron cloud approaches the grid here or here, which is a huge difference. This has been all simulated in full detail, and we see this time shift that's in the order of a microsecond. So here there's still a lot of room for improvement if one wants to conceive a proper design, but we want to stick for that basically to emphasize on the level of details one can see. The number of photons that are detected per electron, of course, follow standard statistics. What I want to highlight is the photon propagation, and there are huge thanks to Igor and Luke from University of Alabama, who provided chroma simulations on that in a Darwin-like detector frame, so 2.6 meters, all filled up with liquid. And what we observe is basically that about 90% of the photons are collected relatively fast. So they follow this exponential behavior with less than 10 nanoseconds. And only a few photons of those detected for the S2 make a long random walk due to Rayleigh scattering and are in the end typically detected at the bottom array, or make a long random walk upside down and are detected at the top. The important point here is that all of the time scales involved here are dominated by the triplet state of the liquid xenon de-excitation. So that's what drives our photon detection timing in this model. Then the end as well, you apply a PNT response, and that's what you come up with. You simulate, let's say, a dual phase where your time the electron has to excite the atom, excite the xenon, is in the order of 1,000 nanoseconds. You get these washed out waveforms. And in liquid, where you only have a few nanoseconds, where your electron transpasses the field that are sufficiently strong, you get these very strongly shaped, strongly peaked signals per electron. And that's what is the striking feature about these S2 waveforms in a single phase detector. So now the question is, how can we profit from this new feature? The first very straightforward idea is, of course, I can count. Yeah, I can, instead of getting my S1 as an integrated value, which is a float and is kind of detached from the number of quanta that are involved, yeah, you can really start to reconstruct electrons. Here it's shown very simple, straightforward. You have a sliding window, identify where you have peaks, and then you look for overlaps, like accidental coincidences of two electrons, which you can identify based on the area and the width in this very straightforward model. Now, if you do that and compare this to the integrated S2 that is shown here, we see that we can reach, even with such a very simple algorithm, a benefit in the resolution. Yeah, so our resolution basically goes down to, for 200 scintillation yields, to the order of 5 to 6%. That's not energy resolution yet. It does not include yet fluctuations in the production of the electrons. That's only the detection efficiency, basically. And if you want to have a more fair comparison, then basically you shouldn't compare the float measurement of the integrated signal, but rather on the quanta level, how many electrons have been involved in this interaction, and there the benefit even looks a bit stronger. Why is this of interest? Because there's a lot of science in this very low energy, like sub-GeV WIMPs on the NR channel or axions on the ER channel. So although this only extends up to 15 or 10 electrons, there is some gain in the physics case. The second point I want to mention is a charge-only reconstruction of the Z position, which of course exploits diffusion. The longer my electron drifts throughout these 2.5 meters, the more it will diffuse, and that's what I can use to reconstruct this. And depending on the number of electrons that are involved in the cloud, let's say 50 or 200, something in that range, I get a more or less accurate reconstruction. Of course, this reconstruction is super coarse compared to the standard S1, S2 time difference drift time reconstruction. But thinking about an S2 only analysis, for example, this would still be an additional independent measure. As well, in a combined measurement where I have an S1, S2, I could make use of that. Sorry, I need that one first. To reject accidental coincidence background, yeah, like basically unphysical events that are accidentally paired, and simply run numbers that shows that for even a rather small signal with limited resolution, 50 electrons, I can reject more than 50% of my AC background with 1% of signal loss. And that is much better than the standard width cut, where basically this arrival time is additionally smeared out by the scintillation timing. What I highlighted here, sorry for that, for the order of discussing it, is this onset here. Yeah, why are we so badly here? That's because here you see these two populations we discussed before. Some of those, the blue ones here, are on a kind of fast track. Some are on a slow track. That's due to the alignment between the hex mesh and the anode wires, and of course, in the end, could be avoided if it turns out to be crucial. The last argument I want to, or last aspect I want to cover is single-side, multi-side discrimination, which is of importance for neutrons. So here you see from xenon wonton data, neutron multiscatter events, and the question is how well in Z can we discriminate between those? Now, instead of looking at a whole waveform where all the statistics from the scintillation process play into a role, in a single phase, we can not only count the electrons, but of course we can reconstruct the arrival time of those electrons as well. And then one can do a simple likelihood test. Does this waveform correspond to more to a single side like event or to a double side event with a certain spacing, like here the 4 millimeters? Yeah. So from the timing we can convert to a Z direction, and if we then define, let's say, a certain fixed acceptance, 98%, yeah, we can simulate true single side events like those here. They still will be reconstructed with a certain Z. And this population, you can define what's your threshold quantile to make sure that you have an acceptance of true single sides of 98%. If you look at basically this threshold as a function of A, the Z position through a detector, and B, the number of electrons involved, where this corresponds, I think, to something like 4 to 60 keV/nr, so covers our WIM search range, then we see that we reach super low, order of 2 to 6 millimeters rejection threshold, which can really help us to get rid of this, one of the critical and potentially avoidable backgrounds for future WIM searches. This brings me to the summary. I hope I've been able to give you a glimpse on the prospects of charge signal analysis using electroluminescence in liquid. I have only covered this part of the benefits that evolve around the fast scintillation per electron, and have avoided to talk about the other benefits which originate from the fact that we don't have a gas gap. Some of those Adam discussed already. What I want to mention is basically that one here, sorry, that by avoiding the liquid gas interface, there's no total reflection, no delayed electron extraction at the interface, and this additionally brings more light collection efficiency and potentially gets us rid of some background components. Thanks for your attention, and I'm happy about questions.
Thank you, Fabian. We have time for 1 or 2 questions. Giovanni?
Hi, thank you. Given also the talk from Adam, I'm just wondering which is the time scale for proving the what you showed today, if there is like attempt to use the facility you have in Freiburg to prove this.
So
and the time scale.
Yeah, I'm convinced that we can get data with the 10 micrometer wire Adam presented so far within this year, and for the next 2 to 3 years, we've foreseen, where the question if there will be funding or not, a larger or a more intense R&D program that as well will include large dimensional tests and stuff like that. So it is an ongoing R&D, and I hope that on the timescale competitive, maybe for Darwin for sure, for another potentially larger G3 detector, there will be, we should have results ready in time.
Okay, thank you.
We have time for 1 more question, Leo.
Yeah. So you said that you can avoid the problem of shadowing by this hexagonal grid. So you funnel the electrons from preferred directions to the wires. Now, I wonder if you're thinking about a very large detector where you will inevitably have sagging on the scale of millimeters, will this not screw up the ability to direct the electrons where you want them to go for shadowing?
So one huge difference here in zagging compared to dual phase is that your electrostatic setting will be basically symmetric. So your net force on the wires will be much lower compared to a dual phase detector where you have this net force downwards. And of course, it's an experimental challenge, even if you increase the grid size here to 5 millimeters or so and have a proper pitch, to avoid or to have this in simulation very nice alignment between two. That's experimentally on a 2-meter scale, super challenging, but I think it's at least possible. Yeah, and everything else we'll have to see in the data, how much in the end the shadowing really plays a role. I mean, the scintillation model we applied includes a shadowing effect, and in the end, I can quickly show that here. It doesn't depend too much whether you approach from here or here, because it's always the same solid angle of emitted photons that will be shadowed. Yeah, the distances here are so small that there will not be a Rayleigh scattering in between. We're talking about micrometers. So I'm not so concerned about this effect, but data will tell us.
Okay, thank you. Thanks again, Fabian. I think we should move on. Next talk is a Geiger geometry single phase TPC. Wingling, are you there?
Yeah, can you hear me?
Yes, you can go ahead.
Okay, so hello everybody, good day. So today I'm going to talk about the potential to use a single phase time approach chamber instead of dual phase TPC in the next generation several 10 ton scale dark matter search. I think I don't need to talk more about the dual phase TPC. Currently, it's the most sensitive dark matter detector for the GeV to TeV WIMP search. The take-home message is basically the TPC has a very good 3D position reconstruction, leading to its very good background rejection capability through the visualization, the single multiple scatter identification, and also it has very good discrimination power using the ratio between S2 and S1. But however, in terms of high voltage and accidental pilot and background, the dual phase TPC may face problem in the next generation multi-10 ton detector, because the anode is in gas, so it is usually grounded or in low voltage. That requires the cathode to be at very high negative voltage. A recent large detector such as 1 ton and the Panax 4 ton all only reached like a cathode voltage less than 20 kilovolts. And accidental pileup is not a major background currently in the dark matter search, because the electronic recall due to the radon is still the dominant one. But as the detector grows larger, the ER contribution from radon is diluted by the larger volume, and also we are developing ways to mitigate the radon outgassing, such as the inverse distillation. But on the other hand, the AC will grow as the volume, since the isolated S1 and S2 rates both grow with the volume. So in the next generation, we may find out that the AC is no longer the sub-dominant one. Probably it's worth a time to have some brainstorming in this stage. So I think for the origins of isolated S1 and S2s, we are more uncertain about the isolated S2s. For the origin of isolated S2s, there are several possibilities. So one is that not all the electrons can be extracted at the liquid surface into the gas. The remaining one will be thermalized and gets trapped at the surface for a long time, like 20-ish milliseconds, before it gets extracted. Also, potential transverse field may further complicate the situation. Another possibility is that the impurities or metals or impurities attached to metals could be photoionized and release electrons. This effect for sure exists, but should be very fast and may not explain the S2s we saw in the data, which are correlated with the big S2s, but with very long time delay. And the third possibility is that the electrons can be extracted out directly from the electrodes. As the field near the wire gets stronger, the tunneling potential is smaller, making it more likely for the electrons to jump out. Also, although in diagram it shows a perfect cycle, a cross-section of wire, but in reality, the wire could have rough texture on the surface, so it may attract some dust and during the operation change the field configuration on the surface, making the discharging problem uncertain and unstable. And in dual phase TPC, we inevitably will have some events happening in the regions between the gate and the anode and liquid surface, since there's no shielding for this region. So S1 is too close to the S2 so that it was not able to be separated in clustering. So the topic of today is trying to postulate a possible distinct TBC geometry, which can mitigate the 1, 3, 4 origins of the isolated S2. So what we propose to try is a single phase time projection chamber with a geometry similar to a Geiger counter. So such TPC is still cylindrical, but with a single wire put at center axis as the anode. Gate wires can be placed several millimeters away from the anode. Cathode wires being placed at the wall of the cylindrical volume, surrounded by the light sensors. When energy deposition happens, the ionized electrons are drifted along the radial axis towards the anode and are amplified through the electroluminescence in the liquid near the anode wire, because all the field lines are focused to the center, which can form a very strong field near the wire surface. Such geometry does not need liquid surface, so the potential trapping of electrons on the surface will not happen. Or secondly, there is a region near the gate where you may still have the scintillation light not distinguishable from its own S2, but since the region is in the center, it's not like the dual phase case. So this GTGPC will have all the signal shielding to ensure a minimal event rate in this region. And finally, because the geometry ensures a field configuration which focuses all the lines from the edge to the center. So the field strength near the cathode wire is not strong, minimizing the electron emission due to the follow Nodenheim effect. However, the GTGPC does trades off the reconstructive simplicity for a more feasible and field configuration. The field along the radial position is not uniform, intrinsically not uniform, so which brings the challenge to reconstruction of the position and the energy. So according to field simulation, such geometry can reach a very high field strength near the anode wire with wires of moderate sizes and not so high the voltage. On the commercial market, I think wires with 100 and 200 micrometer are quite common, which should have sufficient strength to make a big detector easily, such as the future Panax 30 and Darwin. Two simulations were performed trying to with these two wire sizes with gate wires 5 millimeter away from the anode wire. And the gate is grounded. It shows that in order to reach the field threshold for proportional scintillation, the anode voltage are to be 18 and 30 kilovolt for 100 and 200 micrometer wire respectively, which is not so crazy. And under these voltage, the amplification factors are 400 and 800 photons per electron. So if we simply consider we may have a 5% S2 light collection efficiency, and then it is already 20p per electron S2 gain at minimum. The only problem is that the time duration for these two, for the S2 single electron S2 is very short, 16 nanosecond and 31 nanosecond for these two wire sizes, which may cause problem for distinguishing between the S1 and the single electron S2s. And later slides will discuss about it. And here's a full simulation for GTGPC with a detected diameter of 3 meter and 3 meter in height and in radius with 200 micrometer wire, which corresponds to like 30 ton xenon. The cathode is at -1 kilovolt, so that it does not have strong field between the cathode and the PMTs. Gate is at 10 kilovolt and anode 40 kilovolt. The standard deviation of field at radial position are quite stable, I think below 1% level, except for the regions very near the gate and the cathode, which we eventually will throw away for its relatively high background rate. So I think the biggest challenge for this GTGPC comes from 3 aspects, I think. So one is how do we classify between the S1 and single electron S2s, and how do we reach a sufficiently good position reconstruction, and how do we retain sufficiently good discrimination power when the field along radial axis is intrinsically not uniform. For the classification between S1 and single electron S2s, although we said the pulse shape for both are short, but still the pulse shape is different, which can be used to perform the classification. So S1's pulse is contributed mainly by the singlet and triplet decay of xenon dimer, and also the propagation of lights in the detector. Basically, it's a very fast rising, and slow descending. But for single electron S2s, when the electrons start to enter the high field region near the anode, the light starts to generate. As the electron gets closer to the anode, the field strength increases and the amplification factor increases as well. So the single electron S2 pulse shape in principle has a slower rising. So using such pulse shape difference and with the help of deep neural network based algorithm, we checked the classification accuracy for different S2 sizes, as you can see. For very small S2s, for sure, it doesn't work very well, but as the size gets larger, the accuracy can basically reach 80%. So the conclusion here is if we want to minimize the misclassification, we should try to increase S2 amplification. And in addition, the simulation also shows that the sample size of the data taking plays not a major role. Maybe using a 4 nanosecond is already sufficient enough. Okay, so in GTGPC, we are not using the parallel plates as the electrodes. So for sure, we did sacrifice part of the reconstruction quality. The R direction is reconstructed using the drift time, so it is with very high resolution. But the phi position, on the other hand, is lost. But it's not very important since the detector is an axial symmetric detector. But we do want to reconstruct the C position with high precision. The first attempt, of course, is we can use the hit pattern of S2 on the side PMTs. The best resolution we got is at center, which is about 4.5 centimeter. At the top and bottom is quite bad, about 20 centimeter resolution. So we have to find a way to improve. That means in GTGPC, we have to instrument light sensors also on the top and the bottom plane. There are several options, like we can use silicon PMTs or light guides coupled with the PMTs. Both need R&D works to demonstrate, but anyway, if we assume that can work, briefly, the top-bottom asymmetry can be used to simply reconstruct the C. Although it has quite good resolution for the event at center, but it doesn't. It is not capable of precisely determining the position for low S2 and also S2 very close to top and bottom. So, and these are the main goal for the S2C reconstruct, because we actually do not care about the C resolution in the center, but they care more about the resolution at top and bottom in order to reject the surface and external background. So the pattern information has to be used. Here shows 4 hit pattern of S2 with a different distance to top and plane. Visibly, the changing pattern is quite clear. So using, again, the deep neural network, one can also reconstruct the C position based on the pattern information. And we do not care about the resolution center, just at edge. The resolution basically can reach a centimeter and sub-centimeter level. And we actually don't need a lot of light sensor to reach such a, just the sensor to be very close to the anode wire. According to the simulation result, 10 to 10 array with 1 inch in each unit may already be enough. The last concern is whether the non-uniform.
You have 3 minutes left in total.
Okay, thank you. The non-uniform field could reduce detector power to discriminate the ER. So we estimate that both field variance and electric diffusion are the dominant factors for the R resolution, and the R resolution will affect the response. But still, the resolution is at the centimeter and the sub-centimeter level, so it's still minor. We perform the simulation taking this into account. From our estimation, the R resolution and field variance don't play a big role in the discrimination power reduction. The R resolution need to be as bad as 20 centimeters to show a difference. The absolute field strength is still mainly driven. So the rejection power is about 1% to 2.5% if the cathode gate difference is 11 kilovolt. Further increasing the voltage difference, for sure, we will improve the discrimination power significantly, but putting also more pressure on the voltage. Okay, I will skip the summary. Thank you very much for listening.
Thank you. Questions? Giovanni, go ahead.
Hi, thank you very much for the talk. I'm just wondering, since the S2 will produce at the center, for a big scale detector, does the absorption play a big role and for the resolution, for energy resolution, yes, or is still something that you can manage to correct?
Yeah, I think we need R&D work to demonstrate it, but conceptually, since the diffusion is still subdominant, we can calibrate the response at different R, right? So the field is only non-uniform along the radial axis. So if we know the R position, we can try to correct.
Okay. And one question again. Do you have some reflector? If you cannot, are you planning to install some reflective panel if you are not going to install the PMT?
Yeah, sure. By default, all the inner surface without the light sensor will be covered.
Hello, can I ask one question?
Yes, we had time for one or two quick questions.
Yeah, thank you. So there is a concern about chemical polarization of your central wire. So if you have electronegative impurities, they will be sucked towards single wire, and composition of liquid around wire will be different from the rest. So if you have oxygen, nitrogen, or water, whatever, in small concentration, it will be concentrating around wire and may lead to some negative results and like another mechanisms of breakdown or transition to discharge. So were you considering this type of effects?
Sorry, I think I haven't considered it, but I think you are right. Thank you very much for the comment. But I think we need R&D work to try and to debug. Yeah, but for sure, for this kind of detector, we need a very high purity, as you can see.
Yeah, that's yes, my expectations to go to geometry like this. You really need to work hard on purity.
Yeah.
Thanks.
Very last question, Fabian, if it is.
It's super. Whenever seeing radial geometry, I'm worried about maximum drift time. Do you have a number how for a Darwin-sized detector, your maximum drift time from the very largest R to the center would be compared to the 2 milliseconds in a Z drift?
Well, I think it is comparable. I haven't got the number, but since the drift velocity quickly saturated as a function of the field strength, I don't expect a very
but you have this very low field close to the cathode. That's why I'm worrying. I think that's an important argument which we should bring into this discussion.
Maybe a rough estimate about a factor of 3 or 4, I think, in the region of the very low field.
Thank you.
Thank you, Quinn, for this nice talk. Let's move on. Next speaker is Jiangyang Hui, detection of electroluminescence in liquid xenon with the radial time projection chain. Jiangyang, you can go ahead.
You are muted.
Yeah, we cannot hear you.
Oh, sorry.
Okay.
Hi, LIDINE attendants. My name is Jianyang Qi, and I will be presenting a demonstration of a new single-phase liquid xenon time projection chamber developed here at UCSD that is capable of producing electroluminescence in liquid. So our prototypical detector is called Sandix, and its performance will be demonstrated according to the outline above. The goal of this demonstration is to show that signals analogous to those seen in the two-phase liquid xenon time projection chamber can also be seen in this single-phase TPC. This is essentially an experimental test of the detector type proposed by Qing in his previous talk. Sandix is a TPC with a cylindrical volume that uses a 25 micron diameter wire in the center of the TPC as an anode, and a grid of 20 wires around the edge of the TPC as the cathode. Furthermore, it has an array of 8 1-inch PMTs arranged on the side walls and top and bottom PTFE reflector plates. As mentioned in the previous talks, this electrode arrangement is much simpler than that of the two-phase TPC, which uses meshes made of wires. And furthermore, a liquid level between the gate and anode does not need to be maintained, as this is just a single-phase TPC. This detector design essentially shifts the Z coordinate of the traditional two-phase TPC to the radial coordinate R, which is in the direction of the electric field, hence why we call it a radial TPC, or as Ching called it, a Geiger type TPC. Electroluminescence in liquid xenon requires a field on the order of a few hundred kilovolts per centimeter, much higher than the requirement for gaseous xenon, and we can achieve such a strong field due to the radial detector geometry, which causes a field that goes as 1 over R. This gives a very strong field near the anode and is capable of producing an electroluminescence region on the order of a few microseconds to a few tens of microseconds. The left two plots show the analytical field, while the right plot shows a simulation of the field using the Elmer finite element analysis software. As we can see, field lines near the center of the detector are quite straight and in the radial direction, but there are quite a few fringe field lines along the top and the bottom of the detector. And since this detector gives a non-uniform field by design, the design goal of this TPC is to get a field as close as possible to the analytic solution rather than a constant field. So here's an example waveform of a cesium-137 event, as well as a lower energy event. Just as a two-phase TPC, this event shows a narrow prompt scintillation S1 signal and a diffuse amplified ionization S2 signal. Ionization electrons will be more diffuse for events farther away from the anode than events closer to the anode. This diffusion contributes to the width of the S2 signal and causes the correlation between the S2 width and the drift time. So here we're using low width, which is the full width at 10th maximum. So events higher in the detector will have an S2 signal, which is seen more in the top 4 PMTs than the bottom 4. And by top 4, I don't mean that there are PMTs on the top and bottom plates of the PMT, but rather since we only have 8, it's the top 4 in the ring and the bottom 4 in the ring. And so events higher in the detector will have an S2 that's seen more in the top 4 than the bottom 4. And we can define something called the S2 asymmetry parameter, which is the difference between the top 4 and bottom 4 divided by the total S2 area. This parameter is correlated with Z, and we can use this information to select for events near the center of the detector where the field is relatively close to the analytic field, and we can understand it. However, this asymmetry parameter is not uniformly distributed for S2s along Z, as shown by this plot as well as these two plots. And this causes the heavy red concentrations shown in the top right plot, which when projected down to the S2 asymmetry axis is made more clear. Furthermore, you can see that there's a bend on this plot, and this bend is due to the higher light collection efficiency near the center of the TPC as opposed to the edges. We can also reconstruct our information from the drift time as well. However, the drift velocity is not constant due to the non-constant electric field. So this plot right here is calculated by integrating 1 over the drift velocity with respect to the radial coordinate, assuming a perfect analytical field and drift velocity from nest. So this 12 to 14 microsecond maximum drift time does indeed seem to cover most events, as shown in this plot from data. However, it can be smeared out due to factors such as the non-analytic electric field near the cathode, which would cause electrons to drift through a relatively larger and bent non-radial path, which would cause a longer drift time than would be expected from here. But nonetheless, we can still look at events with a short drift time and a small absolute value for the S2 asymmetry to select for events near the center of the TPC where we understand. And we can select for the cesium-137 662 kV gamma line. The effects of the differing light and charge yields for different positions in the detector will give an additional smearing to the population in S1, S2 space, which is not present in the two-phase TPC. Nonetheless, there is still some visible resolution, and we can use the center of this population to get a very rough estimate of G1 and G2 using NEST. G1 is typically what we expect for a two-phase TPC, but G2 is quite low, likely due to the difficulty in producing an electroluminescent signal in liquid. Here's the same plot, but for an anode at 4.5 kilovolts. And I should also mention that the cathode is at -750. We use the same selection criteria, and we see that the S1 value decreases compared to the previous plot, right? And the S2 value increases. G1 is the same, but G2 is still roughly it gets a little higher. Unfortunately, the resolution of the 662 kV peak gets worse at higher anode voltages, but the reason is still not well understood, and we're still looking into this. The median of, unfortunately, the median of the S1 versus log S2 low energy electronic recoil band also shows an increase in the S2 gain as a band shifts upwards for higher voltages. There are some example waveforms for the low energy electronic recoil events, but there seems to be some unexplained light emission, which gives a rather noisy baseline, which can make the detection of small S1s and pairing of small S1s with S2s quite difficult. For 4 kilovolts, this is mostly fine, and we can still resolve an 8 to 9 PE S1, as seen by the coincidence of these 4 PMTs at a time that's roughly 6 microseconds since the start of the event window. However, for a 5 kilovolt anode, we saw that the rate of light emissions gets worse, as seen by the increase in density of these black lines here compared to the 4 kilovolt waveform, as well as an increase in the single PE level peaks in the per PMT waveforms. This increase in rate makes it much more difficult to identify and pair small S1s. So this is sort of a big limitation that we found so far in this type of detector. So in summary, we have demonstrated that the radial TPC works in the sense that it can detect S2s in liquid, give comparable information to that of a two-phase TPC for higher energy events, and is simpler to construct and operate. However, it is currently limited by a low G2 value, a blurrier signal due to a non-uniform field, and the emission of light with a rate that increases as the field increases. The low G2 value still seems to give some good amplification of S2 compared to S1, and some of the non-uniform field effects can be understood to some extent. However, the light emission is still not understood, and our detector sees issues that arise with stronger fields. In particular, it isn't clear whether the light is an intrinsic response of xenon itself to high fields, or if it comes from stray electrons drifting towards the anode from backgrounds. Furthermore, our latest run of Sandix saw some issues with sparking when the anode voltage was too high. So we're currently working on upgrading Sandix to be able to handle higher electric fields. This type of TPC may have the ability to overcome some issues with the liquid gas interface of the two-phase TPC, but it is still in its early stages and needs a lot of further testing. Thank you for listening.
Thank you, Jin-Yang. Questions?
Hi. Can I ask
Hi.
a question?
Hi. Yeah.
What's the electron lifetime level in the detector when you got the result?
So the electron, so typically when we calculate electron lifetime, we look at the S2 versus drift time. However, we can't necessarily isolate the effect of the electron lifetime, because as you go further out in your detector, your S2 size also gets smaller simply due to the smaller charge yield at higher radii. But nonetheless, the purity still seems to be quite good even with this effect, but we can't calculate like an electron lifetime, if that makes any sense.
Okay, but did you see the signal size over the radio position change over time as you purify the xenon? Starting from
initially at the beginning it increased, then it saturates. So basically this detector we operate for many times without even two-phase, and we know the electron lifetime roughly can reach like 100 microsecond level.
Okay, thanks.
Sergey?
Okay, just one very quick question from Sergey.
Yeah.
It's too much responsibility for very good question. What number of photon you can detect for single electron coming to your anode?
Right. So unfortunately, it's still roughly 1 PE per electron. It's very low. It doesn't get past 10.
According to also the G1, which is about 0.1 photoelectron per photon. So we estimate about 10 photon per electron produced around the Y. 10 photon per electron. And then taking into the collection efficiency, then it's about 1 photoelectron per electron we detect for S2. And Sergey, your comment for change a slide about the electronegative impurity stuck on the anode, which might be a reason for producing this kind of light. We can talk further afterwards. And now I was thinking about it.
Okay, thank you. I think we have to move on. Thanks again, Jin-Yang, for this nice talk. Next speaker is Ryan Linehan, understanding the impact of high voltage electrodes in LZ.
All right. Hi, everyone. Can you see my screen?
Yes.
Great. Okay. Hi, everyone. I'm Ryan Linehan. I work at the SLAC National Accelerator Lab with the LZ group. I'm a graduate student at Stanford. Wanted to talk to you a little bit today about the impact of high voltage electrodes on low energy dark matter searches with the LZ TPC. Naturally, I think we want to start out with the introduction slide, but I think it seems like most of us have shown this slide to some degree. So I'll go a little bit more quickly over it. LZ is a low background WIM search experiment looking for low energy dark matter recoils on xenon nuclei. We use a two-phase two-phase xenon time projection chamber design. You get your S1, you get your S2. We have pretty good 3D event position reconstruction using those two, the XY from the S2 and the time difference between the S1 and the S2. And the one thing I'd like to kind of emphasize here is that the compelling piece of this technology is that it's quite sensitive to both single quanta of light and charge. So the G1 for LZ is somewhere on the order of 10%, plus or minus a few. And then the detection efficiency for single electrons is likely to be something on the order of 90%. So this gives a nice ability to search for very low energy interactions with this detector. The typical way, with these detectors, there are a couple different channels for low mass dark matter searches. The kind of canonical one that we use does involve, does require both an S1 and an S2. And that's what, an example simulated waveform is shown in the top here. So you have your S1, some gap, and an S2. These are the zoomed in pulses of those. You can see that the S2 is quite broad compared to the S1. From these, you get your delta T as well as your depth. And with this, you can do some Z fiducialization and carve out a nice portion of your detector to look for, that's kind of quiet in some sense. But for very low energy interactions, you may only get a handful of photons and a handful of electrons too. And the fact that the light collection efficiency is order 10% means that if you're at very low interaction energy, then you may not see any of those photons. However, because the efficiency of observing electrons is still quite high, you still may see the electrons from that interaction despite not seeing the S1. And so from these, you get kind of a different class of event, which leads itself to a different class of searches, where you basically are only requiring that you see an S2. So you no longer require that S1. And while this doesn't, from this event, you don't really get detailed depth information, naturally, because you don't have a visible drift time. But what you can do is you can lower your energy threshold a little bit. And so you can search for lower mass dark matter than the typical S1, S2 search can. Now, the additional problem with this kind of search is that it introduces a set of backgrounds that are not really a huge problem for S1, S2 searches. Namely those from the top and bottom of the detector. And so, the fiducialization in XY is still pretty good because you do have the S2 XY position, but the fiducialization Z is not as good. And so things like interactions near the liquid surface start to become a background, but more relevant for the low energy searches, we believe, are the set of backgrounds coming from the high voltage grids. And for LZ, there are 4 of those. So you have the anode grid, the gate grid, which are both at the top of the detector, and those create the extraction and electroluminescence field. And then you have the cathode and the bottom grid, which are both closer to the bottom of the detector. The cathode naturally creates the drift field, and the bottom grid shields the bottom PMTs from the fields from the cathode. In LZ, each of these grids is a 1.5 meter diameter stainless steel woven wire mesh, which you can kind of see here. This is a picture of the anode grid as completed and at SLAC a few years ago. Each of them is, as I said, a woven wire mesh, which you can see in a little bit more detail here. And just for fun piece of information, I helped build each of all of these grids, and they were designed and built by the SLAC team in 2017 through 2019. Now, these grids, as I said, will produce, and specifically the gate and the cathode. The anode will also create background, but we'll focus on the gate and cathode for now. The gate and the cathode are going to create a number of backgrounds that are kind of annoying for S2 only searches. And I wanted to talk a little bit about what those backgrounds are kind of fundamentally. or what we believe them to be. So there are kind of two flavors as we currently understand them for backgrounds from these grids. The first is field-induced emission. So you have a strong surface field on a cathodic wire, and you can kind of rip electrons out of the wire via a quantum tunneling process. Generally, these don't have associated S1s, but sometimes you can have light associated with gain near that wire. There's also kind of a characteristic rapid turn on of this emission as you inch closer to higher and higher fields. And this turn on has historically limited cathode voltages and gate voltages as well in xenon TPCs, which I'm sure many of you are familiar with. One additional thing to point out, which will be important later, is that you can actually get multiple electrons in your S2 from these events. The Lux detector saw evidence for this, and so it's not only single electrons that are being that comprise part of this background. It's also partial. You may also get multiple electrons emitted. The one problem with this background, or one of the problems with this background, is that it's actually extremely hard to model and predict. So a lot of understanding of this, a lot of building understanding of this relies on testing. Now, the other flavor of background that we deal with on the grids is radiogenic emission. And we believe that the primary component of this is from decay of radioisotopes, daughters of 222 radon that were deposited on the grid wires during construction. All of these will have S1s, but depending on the energy, some will be too faint to see. Naturally, you can get multiple electron S2s created, and this flavor of background is actually quite a bit simpler to model than the field-induced emission. So we'll talk about this a little bit more as we go on. Okay. So I wanted to talk a little bit more in detail about our understanding of each of these backgrounds, and so I'll start with the field-induced electron emission. We actually ran some tests probing this grid field emission in a multi-detector test platform at SLAC in 2017 through 2019. And we learned a few lessons, which were pretty good to learn. The first is that for any given emitter, the time and the voltage dependence of emission from that emitter was hard to predict. It varied quite a bit from emitter to emitter. So we would see some emitters that would emit fairly constantly and some that would kind of just turn on all of a sudden. This is something that we observed on our gate grid and in our gaseous xenon test chamber, but it's also something that was observed by people doing Lux analysis many years ago. Excuse me. The next lesson learned is that a chemical passivation of the grid wires with citric acid actually helps to reduce this emission. And the third lesson that we learned, third major lesson that we learned, was that cleaner grids create less emission. So this is what these two plots here show. I'm basically plotting the XY centroid of pulses that look like single electron emission from our gate in this gaseous xenon chamber. And so you can see a variety of field emission hotspots here. And after this test, we opened, pumped out the xenon, we opened the chamber, we did some other tests and checks. And during that process, we inadvertently added some dust and fibers to the grids, but we also removed some dust and fibers. And so after closing back up again and running again, we saw that several of the hotspots had gone away and some new hotspots had been added. And so this was a pretty compelling piece of evidence to show that removable debris does lead to this electron emission. So that cleanliness is important. But overall, these are some insights we've gained from about field emission. But again, it's a little hard to model. So we'll in LZ we'll actually just have to kind of see what we see and hope for the best, given all the mitigation techniques we implemented using these lessons. However, for radiogenic emission, you can actually do a little bit better of a job modeling this kind of a priori, and so I want to talk about that as well. So this radiogenic emission has a lot of moving parts. So there's the source. We think it's likely to be mostly from the decays of lead-210 and its daughters deposited by well, lead-210 is itself a daughter of 222 radon, and it was deposited on the grid wires during production. We expect some of this lead-210 to be kind of embedded into the wire due to upstream decays of alpha decays that kind of kick the nucleus deeper into the wire here. So there's some layer of embedded daughters that we expect to be present in our wire. So that's something that we have to kind of take into account in our model. This depth is up to about 100 nanometers. So this is, we've incorporated this into our kind of GEONT4 model of this wire background. Another thing which we recently learned was that surface roughness actually plays a role, especially when you consider very low energy S2s. So if the length of the track, for example, a beta track from lead-210 is on the order of the scale of the surface roughness, then you'll lose a substantial fraction of the energy in the metal of the wire rather than the xenon outside the wire. And so taking this into account is quite important for getting that low energy response right. There's other detector response that is more complicated around the wire. The field is much stronger, which changes the light to charge ratio. And non-trivial field geometry makes the response of the gate and the cathode very different. In the gate, you see most of the electrons, assuming they can be extracted, and in the cathode, you actually lose most of the electrons down into the reverse field region below it. So this complicates the picture a bit. And so for this, you actually have to kind of use more fancy techniques like COMSOL and Garfield to kind of get a sense of what the actual, how many electrons survive when a decay happens on the cathode.
Sorry, Ryan, you have 2 minutes.
Great, thank you. And putting this all together, we actually validated this model against some Lux Run 3 data, looking at both the gate grid and the cathode grid. Both of these are S1, S2 data, so we're looking specifically at decays from those grids. And we find that when we allow the embedding fraction of daughters and the overall rate to float, we get a pretty reasonable estimate of, or we get a pretty reasonable match between, at 0th order between our model and the backgrounds for both the gate and the cathode. There's still a little bit of work to be done, but a lot of progress has been made. Now, what we, and this is in the kind of quote unquote high energy regime, so under 60 keV or so. But what we really care about is this lowest bin of these plots are S2 space, basically, and a number of electrons in the S2 is on the x-axis. What we really care about is the number, the response in this very lowest bin, or maybe the very low, 2 lowest bins, because that's where our S2 only search is going to happen. And we can also, so what we can do is we can extend our model to that lowest energy region and compare to Lux as well. This time it's S2 only, not S1, S2. And so we find that the grid radiogenic background is likely to be the major contributor or a major contributor to this S2 only spectrum down, below about 50 electrons here, which is very low. The gate grid contributes most heavily to this background, but it can also be more easily removed with S2 shape cuts. And the surface roughness, again, is critical to getting this shape right. And so looking forward, that's something that we have to kind of take into account. So there's a lot of work to be done, especially below about 10 electrons, where other effects may turn on. But overall, we have this model that seems to describe S2 only backgrounds fairly well down at low energies. So just to sum up, backgrounds from LZ's grids will be critical to understand and mitigate for an S2 only search. These take on 2 flavors: field emission backgrounds, which are kind of hard to model, and radiogenic backgrounds, which are a little easier to model, and which we've successfully shown to fit to recent Lux data. So thanks for listening, and I'm happy to answer questions.
Thank you, Ryan, for these nice results. We have time just for one urgent question. Sergey?
Well, thanks. Like one thing is, comment is that likely you have more flavors than 2, because in metal, dislocation motion can, like if it deformed or you have stress, can produce excitations in the oxide layer and result in emission of photons and electrons with non-zero energy. But my question is, you make a statement that you believe that emission from electrodes are the main source of this few electron events. Like, what arguments you have to prove that, or why you think so? You also have unextracted electron on liquid surface, and you have some bulk impurities which can make this. So why you are saying that it's a surface of electrodes?
Right. So here, I think I might have kind of I might have come off as saying too strongly that those are the contributors, the only contributors to say this rise. But you're absolutely correct. There's going to be more than just those. You know, I think a low level, high levels of this field emission can high levels of this field emission can create this spike, you know, in isolated hotspots. But those were removed for this Lux analysis. And so I think what we're seeing here is some low level contribution from field emission. But here in the ST only plot, I'm showing not only the contributions from, or the Lux data is not only showing contributions from the grids down below about 10 electrons, but it's showing all the stuff that you said. And so, you know, thinking about the grid contributions, you know, I was saying field emission and radiogenic emission, but certainly there's more non-grid backgrounds below 10 electrons as well. So, and above 10 electrons. So yes.
Thank you. Sorry, Fabian. If it is a very, very quick question, otherwise you can write in the chat the question and
I'll take it.
Thank you. Thank you again, Ryan. Next speaker is Reid Watson. Latest results from the xenon breakdown apparatus. Reid, are you there?
Yeah, sorry, I was fiddling with Zoom. Hi, everybody. My name is Reid Watson. I'm a graduate student at UC Berkeley, and I'm here to present the latest results from the xenon breakdown apparatus.
Sorry, Reid, we cannot see your screen.
Oh, you can't?
I cannot see.
Yeah, I cannot. Can you share it again?
Oh no, my Zoom is messing up at the moment.
I can share for you, and if you need, let me see.
Yeah. I guess that's what we'll have to do, or switch with the next presenter.
Yeah, if you, maybe we go ahead and then you start from scratch Zoom.
Yes, is that possible for the next presenter?
Logan, are you there?
Yeah, it should be okay. It's okay with me.
If you don't mind, you can present before Reid.
Okay.
Your talk is the electric strength of noble and quenched gas for high pressure time projection chamber. Thank you, Logan. Go ahead.
Can you see my slides?
Yes.
All right. All right, so yeah, so hello, my name is Logan Norman, and I'm an undergraduate that works for the New Res group at the University of Texas at Arlington, and I'm going to be talking about some of the DC voltage breakdown studies we've been doing. So as a quick note, if you wanted to see anything I present here in more detail, we have published a paper and it's on, sorry, it's on arXiv. The link is in the slides. And so we were looking at these gas breakdown shrinks, mostly because we worked on an experiment, on the next experiment, which uses high pressure xenon gas alongside these high voltage components. And so for detector design, it's kind of, it'd be really nice to know the breakdown strengths of these gases, so you know how far away to put the high voltage components from sensitive electronics, right? And the same can be said for the Dune MPD. They, in particular, were looking at considering using a mixture of like 90% argon and 10% of another gas like CO2, CH4, CF4. And those mixtures are kind of strange, and the literature isn't out there up to high pressures for like the breakdown strengths. So it'd be nice to be able to theoretically predict different mixtures of gases at different pressures and know the breakdown strength of those gases, right? And so we set out to do that. And today I'm going to present basically our experimental results we've collected, as well as the new theoretical model we have come up with to theoretically predict these breakdown strengths. But first, I wanted to kind of explain some of the other models we'll be comparing to. And so these two equations are a good place to start. The one on the left is Townsend's first ionization coefficient for alpha, basically, and alpha is like the amount of ionization possible over a certain length. And he basically approximated this alpha using an exponential term where A and B are these empirical constants based purely on whatever gas you're using. And he relates alpha to the pressure and electric field, right? And then the equation on the right is Townsend's actual breakdown criterion. So this signifies when a breakdown occurs. He sets this e to the alpha d term equal to basically a constant. This gamma c is simply a constant. And so what you can do is you can take this approximation for alpha on the left, plug it into this alpha on the right in the breakdown criterion and rearrange a bit. And then eventually you get this equation that relates the breakdown voltage to pressure and distance, where A, B, and gamma c, those are all constants. So pressure times distance is pretty much the like independent variable here. And from its creation, this law was only valid in a certain region, mostly because it was made using that approximation for alpha. And that approximation was only valid in a certain region of, a certain region of E over P, electric field over pressure. And so this didn't really capture all the regions necessary to predict breakdown strengths, especially up into the high pressure region up to 10 bar. And others have tried to come up with different theories. One notable theory would be the streamer breakdown theory, which kind of takes into account some space charge effects. So basically, this is a picture of how a streamer forms. There's like initially a burst of electrons that ionizes some of the gas molecules in between the electrodes and creates this positively charged ions in between here. And then the streamer forms from the anode and kind of drifts toward the cathode, and at the head of the streamer there's a high electric field, and basically a streamer breakdown occurs when that electric field created from the space charge at the head of the streamer is equal to the applied electric field. And so people were working on this, and they sort of calculated that it should be a streamer breakdown is likely to occur whenever this e to the alpha d term is equal to 10 to the 8. Basically another constant. I listed the Townsend criterion here to kind of show you the similarities. They basically both set this e to the alpha d term equal to constants. And so they thought that this meet criterion would kind of explain another mechanism at high pressures and extend the theory up into high pressures. However, when we looked into it, we really couldn't find many papers citing the validity of either of the Townsend criterion or the meet criterion up into the high pressure region up to 10 bar. And so we set out to kind of characterize that region ourselves and take some data to try and then compare to the theoretical values. And to do that, we made this little setup here. It's pretty simple. We have a cathode on the right, anode on the left, and we can set the distance very accurately between them. And this whole thing gets put inside of a pressure vessel that we can evacuate out, fill to whatever gas mixture, whatever pressure we need. And then, and so these are the results we got in argon, and we used argon as our initial testing because if you remember, that approximation had those A and B constants. And so those are very well found in the literature for argon. You know, they're in many places and they're easily found, and we can use that to compare to the theoretical predictions. And so we took these measurements in argon. This is our largest data set. We went all the way from 0.1 bar up to 10 bar, and electrode separations of 0.1 millimeters up to 10 millimeters. So we tried to cover as wide a range as we could with our setup. And then we compared it to the theoretical values, where the blue line here is the passion curve made with the Townsend criterion, and then the orange line here is the passion curve made with the meet criterion. And as you can see, according to the theory and in the literature, the passion curve has been shown to be very accurate in that region where that approximation is valid. And so this is sort of that region where it is valid, and you can see it matches the data very well. And then there's this divergence up into the high pressure region, where there's very large differences between the theory and the data. And since it's on a log scale, these are even larger than they would seem. And they even seem to kind of diverge on completely different slopes as well. So we weren't very happy with how the theoretical predictions performed here. And so we decided to try and make our own model that would be able to accurately predict the breakdown strengths in a very wide range. Our group just so happened to be working on a program called PyBolts, which is a Python version of the MagBolts code. And what it does is it calculates gas transport properties such as, you know, diffusion and stuff like that using Monte Carlo simulations. And the plot on the left shows basically the accuracy of the PyBolts code as opposed to data for the alpha term, because it just so happened to produce the alpha term, which is kind of what we needed. And the plot on the right, we did to kind of compare what PyBolts predicts versus that approximation I showed earlier. So the red line here is that approximation, and the blue line and the blue dots are what PyBolts predicts for that alpha, Townsend's first ionization coefficient. And as you can see, it's very different in many of the regions, except for a small region up here. It seems to be very close. The approximation seems to be very close to the PyBolts predictions. And so what we did is we took this data for alpha directly from PyBolts, and we plugged it into the Townsend criterion and meet criterion, and we got these curves out. So the important curves to look at here, the new curves are the purple and the green lines, and they're plotted as bands because if you remember those the Townsend and meet criterions, they set them equal to constants. Well, in the literature, we found variation in those constants, so we just plotted a pretty wide range for those. And as you can see, it doesn't affect it too much anyways, so that worked out. But if you look here, the argon data matches the PyBolts, the Townsend criterion prediction using PyBolts data. And so the PyBolts Townsend prediction matches the argon data very well. And we were very happy about that. But if you notice, the meet criterion, this is the green line here is the PyBolts meet prediction. And the orange line as well didn't seem to match the data at all anywhere. And we thought that was strange until we started testing other gases. Specifically, when we started testing quenching gases, we noticed such as CO2, which is this plot is for CO2 here. Quenching gases tend to follow the meet criterion predictions using the PyBolts data, of course, but the meet criterion predictions instead of the Townsend. They aren't even close to the Townsend prediction. And so, yeah, we noticed that the noble gases that we tested all followed the Townsend prediction, and the quenching gases all followed the meet criterion predictions. And then we proceeded to test a bunch of other gases to see if what we were thinking holds up. And we tested argon, xenon, CF4, CO2, and then we tested some argon mixtures, which were kind of representative of those dune mixtures that I mentioned earlier. And so these are the results for argon and xenon, both noble gases. And you can see they both follow the Townsend prediction fairly well. And the Townsend prediction reproduces these very well. And then CF4, another quenching gas, follows the meet criterion prediction, the PyBolts meet prediction, quite well, as opposed to the Townsend criterion prediction. And then when we looked at the mixtures with argon, they tended to be somewhere in between, which is kind of what we would expect. You know, if you mixed a quenching gas and a non-quenching gas, the breakdown strength is somewhere in between the two PyBolts Meek and PyBolts Townsend. And then these are other mixtures, and as you can see, they are also in between. The CH4 one is almost perfectly halfway. And then at the very end, basically, our feed through was only able to go up to 50 kilovolts, but we wanted to find numbers for all the gases at 10 bar 1 centimeter. And so we projected the breakdown voltage out using our model and got numbers for all these gases at 10 bar 1 centimeter. And of course, the noble gases, argon and xenon, should follow the Townsend numbers here very accurately. And then the CO2 CF4 should follow the Meek numbers here. And then the others should be in between the numbers listed in this table. And so just a quick summary. Basically, there's been a lot of work on this breakdown, on breakdown strengths of gases by theory and experiment, but not really a lot of them have gone up into the high pressure region. And so we decided to take a bunch of data all the way up into the high pressure region and beyond. And both the traditional Townsend-Meek breakdown formalisms, they kind of weren't accurate at all up in the high pressures. And so we developed a new model from first principle theoretical predictions. And that model was very accurate and was able to reproduce the data nicely, with the Pie-Boltz-Townsend criterion being accurate for the noble gases, and then the Pie-Boltz-Meek criterion being accurate for the quench gases. And also we have uploaded example code for simulating the breakdown strengths of whatever gas mixture you would like in the Pie-Boltz-Git repository. Thank you. That is that.
Thank you, Logan, for this nice talk. Any questions for Logan? Florian, please go ahead.
Yeah, hi. Thank you for the nice talk. I have one quick question. I was wondering about the amount of impurities in the noble gases that you were testing. Do you think the purity level does play a role in the breakdown occurring or not?
Yes. So we used the highest purity we could get in most cases. And so it was usually ultra high purity of gases. But yes, the impurity does play a role. And I believe if it has like air or water, depending on where it sits, as opposed to like, so if it's above the air or water, it will bring the breakdown strength down. And if it's below, it'll bring it up, depending on where it sits, of course. And so, yeah, that's what the impurities would do. But in most cases, we use very high purity, and we evacuated out the vessel to a pretty high vacuum beforehand. So it shouldn't have taken much effect, I believe.
Okay, thanks.
Any other urgent questions for Lou? If not, let's thank Logan again. And Reed, did you manage to fix your problem?
I think so.
Try to share again your screen.
Can people see this?
Yes, very good. You can go ahead.
Okay, and can people see this?
Yes.
Okay, great. Thanks for your patience, everybody. I have some videos embedded that I really wanted to show. So hi, everyone. I'm Reed. I'm a graduate student at UC Berkeley, and I'm here to present the latest results from the xenon breakdown apparatus. What I'm going to talk about is the Zebra test stand itself. I'm going to discuss some various breakdown mechanisms in liquid xenon. So the previous talk is a good primer going from gas to liquid. I'm going to talk about specifically how we analyze the data in Zebra, and then I'm going to present some results on the various contributing factors to electrostatic discharge in liquid xenon. And at the end, I'm going to give some indications of warning signs preceding a breakdowns in liquid xenon. Zebra is the xenon breakdown apparatus. It's a 5-liter spark chamber that we fill with liquid xenon. It contains a pair of Rogowski electrodes, which have the main property of having a very large uniform electric field between them. You get a more uniform field over a larger area than spherical or planar electrodes this way. And the way we control the surface area that is exposed to high electric field is by moving the anode up and down with a linear shifter. We control the gap distance and the stressed area at the same time, so we have a degeneracy there. In addition to just recording the voltage where a breakdown occurs, we also record a lot of other information about what's going on in the xenon at the same time. The main things we have are a light sensing circuit. So we have one of 3 things at any given time. We have high-speed cameras that are looking at the gap between the electrodes. We have a silicon photomultiplier in many of our runs. And occasionally we turn on a photomultiplier tube in order to be very sensitive to single photons during a high voltage ramp. We always are recording the current through the high voltage power supply, but due to sampling and just general precision errors, we also record the current going into the anode using an AC coupled preamplifier. And the main operational loop of Zebra is a typical breakdown test loop where we ramp the cathode to a high voltage at a set ramp speed. And then when the high voltage power supply current exceeds a set point, we ramp down to 0 and we just record the peak voltage. And we purify the xenon through a combination of chemical inline purifiers and a getter, and we test the purity using a liquid purity monitor, so just a miniature TPC, and we get between 5 and 50 ppb oxygen equivalent impurities within our system. So dirtier than LZ, but cleaner than you can get out of the bottle. Breakdowns in liquid xenon. It's been known for a while that you get breakdowns in liquid xenon much lower than you would expect based on just naively scaling the density of gas data. So there's a few reasons for this, but mainly you get multiplication at around 700 kilovolts per centimeter, but you end up seeing these breakdowns way before that. The main mechanisms you expect are the typical relationships from the previous talks, such as avalanche and impact ionization, and you would expect some sort of scaling with separation distance there because you would have more opportunities for impacts to create additional ionization. And a review of that goes on there. However, you can also achieve these streamers, which is what we believe are happening, which follows the rather meek criterion that the previous talk talked about. But additionally, a major theory about how these breakdowns progress is gas bubbles. So you may have simply random gas bubbles dissolved in the xenon, or bubbles that form on the surface of the electrodes, or they form elsewhere in the system and they float in between the surfaces. And of course, gas is much weaker than liquid, even when you take into account the density scaling. So you don't want gas anywhere near, and also the gas bubbles will concentrate the field lines. Additionally, you could have gas bubbles appear by superheating the liquid and then rapidly causing bubbles to nucleate over a short time scale. Possible contributing factors are anything that will either increase the field or increase the distance that an electron goes between impacts. So surface roughness has been discussed. If you have small protrusions on the electrodes, then they can enhance the field by up to like a factor of 1,000. So you can definitely achieve high fields that exceed the multiplication threshold. Stressed area is the main thing that Zebra is concerned with, meaning if you integrate over a larger surface area, you get a larger probability for these asperities. So you'd expect some sort of scaling with bigger electrodes being weaker than smaller electrodes. Separation distance, of course, feeds into the normal Paschen theory. Ramp rate is an additional question that we want to answer, which I'll discuss later. Purity, of course, more electronegative impurities means more electrons being absorbed before they have a chance to create multiplication. Another factor that we investigate in Zebra is pressure, which will affect the ability for gas bubbles to nucleate. And we have previous results here. And here's an actual picture of a breakdown occurring in Zebra. The main analysis consists of examining the data coming out of our PLC. The high voltage power supply is ramps in discrete steps of 100 volts. And we just keep doing that until we get a trip. And when we get a trip of a high current through the power supply, we record the peak value and as the breakdown voltage. And the main thing that we do to select to clean the data is that we require that the breakdown occur at least one sample away from these steps, because we expect that we want to be able to test the ramp rate, and we can't test the ramp rate if we're like sensitive to how fast the high voltage power supply is going between these two samples. And additionally, we select out our desired pressure, and we exclude the first 10 breakdowns of any data set under the hypothesis that some sort of conditioning might be going on. And as you can see, we're justified in doing cut number 1 because most of a higher number of breakdowns are occurring close to the steps versus far away from the steps. Stressed area is one of the main variables that Zebra investigates. SEA is the usual abbreviation, and this is defined as the surface area on the cathode such that the E-field norm is greater than 90% of the maximum E-field norm in the system. We simulated these using Phoenix and extracted these stressed areas at various cathode separations. And additionally, our cathode has a somewhat uncontrolled variable, which is the angle relative to the anode. So in addition to the separation distance, we also simulated the tilt angle in order to have that as a floating variable. And over here, you can see that as you increase the separation distance, you increase the stressed area in a roughly linear way when you until you get to very small distances where it becomes a little bit nonlinear. So the general analysis that you do here is a weakest link analysis. So essentially you extract the cumulative distribution, and then from there you get the survival probability, and from there you get this function capital H, which is called the cumulative hazard. And this is a number which expresses the expected number of trials that you have to do in order to get to a given variable X, in this case, a field. And the derivative of this is a differential failure rate, which is a little bit easier to conceptualize, which is like the probability of failing while increasing X by some discrete amount. The general fit that we do is to where the hazard function is equal to the Weibull distribution, which is simply a power law in X. Additionally, we saw evidence that we have multiple components, and the reason why we think we have multiple components contributing to breakdown, so meaning different mechanisms, is because when you do this double log plot, you expect a straight line for a pure Weibull, but in a combination, you can see bends and knees in this plot, and we saw bends and knees, so we switched to doing a multi-mode Weibull distribution where you simply sum the cumulative hazards. So the results of Zebra are plotted here. We did a maximum likelihood fit, and we took the larger Weibull component. So we did the multi-mode, and we said, okay, the bigger one is probably the really testing liquid xenon, and the lower one might be systematics in the system, was our general hypothesis. And we are only using data from the latest run of Zebra using polished electrodes that we were confident don't have any asperities on them, and I might get to discuss that later. You might notice very large error bars. This is because we don't have very tight constraints on the cathode tilt, and improved image analysis will decrease those error bars in the future. So from here, we extract a power law relationship with stressed area, where roughly the power is a negative 0.2 here. So as you increase the stressed area, you decrease the expected breakdown field. And we are roughly consistent with earlier SLAC data. They have quite large error bars, but we generally are able to scale to within a few sigma of their data. Another thing that we tested in...
Sorry, you have 2 minutes.
Okay, so we tested passivation. It's roughly consistent. Passivation is something that's done in LZ. We additionally tested pressure dependence. So essentially, we were able to control the pressure by controlling heaters and the flow rate through Zebra. And we found that there's a possible modest increase in breakdown field as you decrease pressure, which is the opposite of what we expected, but also the error bars are quite large. So we wouldn't conclusively say that we saw a pressure dependence. Additionally, we tested the ramp rate. So we went from 6 kilovolts a minute to 12 kilovolts a minute. And we saw a modest increase in breakdown field in the case of passivated and sort of this inconsistent bendy relationship with the normal polished electrodes. You would expect based on just doing the math that increasing the ramp rate will increase the breakdown field just because you are exposed to high fields for a shorter amount of time. So you would expect the green curve. But we expect that really what's going on is you're heating the electrodes more. So the relationship might become more complicated as you increase the ramp rate. And the main thing that I want to show is that if you're worried about breakdowns, you generally get a little bit of warning signs. In Zebra, we see a gradual increase in the current, both through the power supply and heading into the anode immediately before a breakdown. In addition, we also see some light on a much shorter timescale, which makes it harder to adjust, but about 300 to 400 microseconds before a breakdown, you start to see an increase in light production. In addition, to the linear ramps, we also did a static ramp where we ramped to a voltage we deemed safe, and then we just looked at the PMT while this happened. And we saw that for minutes at a time, we were getting increased light into the PMT before it eventually settled down.
Sorry, Reed, time is over, unfortunately.
Okay. Right. So we also see various qualitative results that indicate that heating of the liquid is the main reason why you see breakdowns lower than you think. Basically, the bullet point conclusions are that increasing your stressed area will decrease the breakdown field. We didn't see any dependence on pressure. We saw a modest increase based on ramp speed, and passivation didn't seem to help all that much. Thank you. I will answer any questions y'all have.
Thank you. We have only time for a very quick question. Sorry, I just had to take the first one in line, which is Sergey. Please go ahead, only if the question is...
Just one. It's a comment going into question. So people were studying the memory effect of breakdown in gas or afterglow in the gas. So there is a dependence on probability of breakdown from the time elapsed from the last breakdown of discharge. And this is connected to impurities and long-living excitations, which can produce initial ion or electron. So were you trying to look at effects like that?
We were concerned with the amount of time between breakdowns, yes, but mostly we were concerned that the bubbles that get created following a breakdown had enough time to clear themselves, so they didn't affect the next breakdown. Mostly we had that set to around 30 seconds between when a breakdown occurred and when the next ramp started. But of course, each ramp took about a couple of minutes, so the time between breakdowns was quite large.
Okay, thank you. And let's move on to the next speaker with Luca Pagani.
Hi,
High
everybody.
voltage cable feature concept for future dark matter neutron experiments.
I hope you can see my screen and you can hear me well. So
Yes,
today,
yes.
what I want to talk about is new high voltage cable feed-through concept that will be used for next generation dark matter neutrino experiment. This work is done in the context of the dark side collaboration. So, okay. So as you know, next generation experiment that are using noble gas will become bigger in size, and so also their need for high voltage. In particular, if we look at the TPC, let me remind you a little bit how it works. And here on the right, you have nice conceptual design for the dark side 20K. So in order to be a particle detector, we need an electric field inside the TPC. And because the field is created by anode, cathode, and the field cage. And the main thing is that we need to safely deliver the high voltage to the detector. And this is done, just to remind you, by the high voltage feed-through, which basically is a device that can penetrate the cryostat and is specifically designed not to create a breakdown in the cryogen, which can be, liquid argon or liquid xenon. What is a breakdown? Read just tell you about. Here, I'm just showing you a couple of examples of traditionally designed feed-through that works. We have the proto-dune, we have the dune one, and also we have a small one which was used for DarkSide 10, which was the precursor of the DarkSide 50 experiment. So let me move on and try to tell you how traditional conventional design feed-through are made. They usually couple a metal that you can see here, which is the core, or the ground to an insulating polymer. And this cartoon here show you a little bit the various components. We usually have the strong field strand located at the end of the ground ring. And in order to avoid a breakdown, those feed-throughs are sized using the relationship existing between the electric field and the distance from the central conductor that I am pointing here. So basically, the electric field is proportional to 1 over the distance. So you can size up your feed-through in such a way that it doesn't, the electric field doesn't exceed the field strength on the material. To see this in a more practical way, let me show you here a constant simulation for 9 volt of the field strength in liquid argon for a traditional design feed-through as a function of the distance from the inner conductor. Basically, I biased the feed-through at different voltages, and I try to see what was the distance at which, let's say, you get a field that is exceeding the breakdown voltage. Just to have an idea, if we want to deliver 600 kilovolt in liquid argon, you need to have a high voltage feed-through with an OD of around 10 inches, which on one side is very massive and can be constructed, but it could not be easy. Also, it doesn't solve some problem which can arise from the fact that we are using two different material, metal and a plastic, which can have different thermal contraction, thermal expansion coefficients. So from here, we try to think about a new concept for a high voltage feed-through, which basically is a cable, a coaxial cable, with the exception that has an extra layer, which we call it a semi-resistive layer. So the feed-through is a co-extruded multi-layer coaxial cable, which will be made of a single material. And this semi-resistive layer basically has the function of keep confining the electrostatic field and preventing the background. The available parameters to tune this semi-resistive layer are both the thickness of it and its resistivity, and there exist various solutions to build this kind of material. Just to show you what is the parameter space that is allowed for this extra layer. This plot shows you a Compson simulation in the plane of thickness, dt of the semi-resistive layer and its resistivity. This plot is application dependent because you need to know the bias voltage at which you want to bias your feed through, and also the dimension of its feed through. As you can see, the allowed region is comprising in this, let's say it's basically a band. On the right side, the band is limited by the fact that we want a high voltage feed through, so we don't need to exceed the breakdown voltage of the argon. And on the other side also, we don't want to create bubbles inside the cryogen. And in particular, the left-hand side limit is due to the fact that we don't want to nucleate any bubble. So we are requiring a power dissipation of less than 1 milliwatt per centimeter square. So this is the parameter space. So let me just briefly mention a couple of ways in which we can achieve this semi-resistive layer. The first one is using a semi-resistive polyethylene. So as you can see from the plot here on the bottom, it has been found that adding carbon blacks into polyethylene make it conductive. But as you can see, the conductivity of the polyethylene as a function of the concentration of this carbon dot is nonlinear. Even if it's practically difficult in tuning the content of carbon, we think that it's feasible to find the right resistivity for our semi-resistive layer. And once you identify this material, you can just send a bunch of it to the cable producer, and then the cable producer can co-extrude this extra layer on the cable. On the top, I show you some samples that we obtained from a company that is doing this kind of process. Another way of creating the extra semi-resistive layer could be ion implantation. As you can see, again, modifying the surface of polyethylene with ion can create conductivity. Again, the resistivity is a function of the fluence. The number of ions per centimeter square that you are implanting is non-linear. Still, we think that there is possibility in tuning both the fluence, the energy of the particle, in such a way that we can achieve the right resistivity required for the semi-resistive layer. This avenue is a little bit more challenging than the previous one, because once you find the right recipe, yes, you need to build in your lab, let's say a vacuum chamber where you can basically irradiate the tip of your cable. But again, it could be possible. Here I'm showing you some samples that we sent to be irradiated with various fluence of argon. As you can see, they are kind of toasted, but still measurement of their resistivity is ongoing. The third way that we can achieve this extra semi-resistive layer can be using semi-resistive epoxy. Again, is very similar to the semiconductive PE. Those epoxy can have a different content of graphite that can be tuned. The only thing that I have to mention for here is that you need to etch the polyethylene in such a way to create a strong bond between the epoxy and the polyethylene. You can see how this look like after the epoxy is applied. Again, some R&D needs to be done here to assess the efficacy of the etching, and also to try to find a way to create a very uniform and thin layer, which can will not peel off while doing a thermal cycle in the cryogen. So those are the three main possibility that we saw so far. What's the work ongoing? We are testing a commercial cable made entirely of polyethylene, which can be our first possibility to start developing this new high voltage cable feed through, even if this cable doesn't have an extra conductive layer. In parallel, we are doing some R&D in trying to test the various options. And here you can see on the picture a lot of let's say a lot of the R&Ds that we are working on. I'm not the only one working on it. Are working with me, in particular Tyler and James. Also, I need to thank Knut from Slack, because he provided us also a lot of insight about how to use this commercially available cable. So let me just conclude with timeline. We think that a preliminary version of the voltage cable feed-through can be used in the DarkSide program, and let's say I have maybe to revise this 2022, but let's say I guess late 2022 can be a good date for this. The final version of this cable of this high voltage cable feed through for sure will be used in DarkSide 20K program, and is foreseen for 2024. And that's it, and I can take questions.
Thank you, Luca, for this nice work, for being on time. Let me just remind you to upload the slides to Indigo, because they are not still available. There is also a question in the chat from Mika. I think this question is for Reed. Reed, if you can answer in the chat. Question for Luca.
Luca, I had a quick question. Thanks for the talk. So, I mean, just based on sort of the ongoing work that's gone so far, when you scale this up, do you see this approach potentially being easier or cheaper relative to conventional high voltage feed throughs, or do you think it's going to be more difficult, or is it hard to tell right now?
Let's say, I think it would be feasible for higher voltages. Like the idea is that you don't want to have a 10-inch high voltage feed through to penetrate your detector. Here, I guess with maybe 1-inch cable, you can accomplish the same. It's just a matter of tuning this. Let's say there are a lot of handles and parameters that it can be tuned, like the inner conductor or the insulator also in the cable. Is not, what I show you is because I started from a commercially available cable, this one, and basically I start working on that because it was the only one available. But speaking with the company, you can there is more room than what I show you right now. The only main thing that you need to work on is this, finding the right concentration of, for example, carbon dot in this polyethylene to find the right resistivity. And yes, I think it will be cheaper because just you ask a company to create 1,000 feet of cable, and it should be cheaper.
Any other question? If not, let's thank Luke again, and let's move on to the next speaker, Matthew Breslin. Low threshold operation with simulation with scintillating xenon bubble chain. Matthew?
Yes. Hi. Let me just get a laser pointer. Okay. So hi, I'm Matt. I'm a PhD candidate at Drexel University working on bubble chambers, particularly with SBC, the scintillating bubble chamber collaboration. So I'm going to talk about the final results from the xenon bubble chamber. So first, I don't think I need to say much about noble liquid scintillation, but I do think I should give some brief words on bubble chambers. So bubble chambers work by taking a fluid, making it superheated, and you wait for a particle to come in and deposit a little energy and overcome this potential barrier and start to boil. Historically, there are kind of two types of bubble chambers. If you've seen pictures, in the particle physics textbooks or just historic pictures from bubble chambers, you've probably seen the tracking bubble chambers. These are dirty bubble chambers, just meaning that the fluid isn't particularly held against very clean, pristine surfaces. It's mostly just against metal. So it'll start to boil pretty much right away. They only needed to be superheated for a few milliseconds to catch a beam spill. And the particle physics was done looking at the tracks. You'd see the beam come in, see a vertex, and then see all the tracks. If there's a magnet, they curve around, and you do your particle physics that way. So you didn't really need to know the bubble creation threshold, except for maybe to do a little bit of particle ID. But nowadays, we operate clean chambers for dark matter searches. You've probably heard of PICO and now SBC. Where we keep the fluid against a very nice quartz jar so it can be superheated for minutes at a time until you get a nuclear recoil. And then you just get one bubble, like a WIMP signal or a neutrino signal will just be one bubble in the bulk. And so your particle physics is kind of held up in that bubble creation threshold, which is called the Sandix threshold. It's a function of pressure and temperature. And if you get multiple bubbles, it's probably a neutron multiple scattering. Worth saying, this isn't a scintillating bubble chamber, but it is a bubble chamber that I've operated with Freon. So the xenon bubble chamber is, or was, one of these small test chambers, a clean chamber with about 30 grams of liquid xenon. Eric Dahl presented about it at LIDINE a few years ago. So that went into one publication. And then there was some more data taken afterwards, which is what I'm presenting now. Previously presented was Sandix thresholds kind of high, around 10 keV, 8 keV for this kind of result, showing that you could get nuclear recoils around 20 keV. But now we've operated it down to, say, half a keV. And we have evidence of nuclear recoils below about 5 keV and no sign of electron recoil nucleation at any threshold. So that is important. So starting off with this intrinsic electron recoil insensitivity, xenon bubble chambers are remarkably insensitive to electron recoils in the bubble nucleation. Of course, you do see the scintillation if you have an electron recoil event, but you don't get bubbles. So Glaser, who invented the bubble chamber, tried to operate early bubble chambers with xenon and couldn't get tracks until he added ethylene, which quenches the scintillation, and then you can get tracks. But with pure xenon, no tracks, and in our case, no extra single bubble events in the bulk. So in this xenon bubble chamber data, we used 3 different gamma sources, the strongest being about 0.5 millicurie yttrium-88, which is the green points on this plot. And with any of these sources, we don't see any increased rate of bubbles against background. So these are all 90% confidence level upper limits, except for one interval that's just barely an interval. And with this many points, you might expect that. So again, the green points here are the strongest source. So they are the lowest in terms of bubbles per gamma interaction in the chamber. Upper limits in the x-axis here is Sandix threshold. So you see that we've operated down to about 0.5 keV Sandix threshold. The square points have background subtraction. The circle points, there's not enough statistics in either the source data or the background data to do a fair background subtraction, so we present it without background subtraction. And you can see that at better than 10 to the minus 7 bubbles per gamma interaction, we don't see anything. This black point is what was presented in the initial paper, the first data, at about 4 keV. And then to detect WIMPs, of course, we need to calibrate nuclear recoils. So here's some neutron calibrations. First, photoneutron source, that same yttrium-88 source with some beryllia. This is pretty hot, so we get about 850 neutrons per second. And this does produce a rate above background. So we know that it's not the gammas from the yttrium, from what I just showed, but the neutrons are making a rate above background. The endpoint for these 152 keV neutrons is about 4.9 keV on xenon, which means that seeing any rate at all means that we are seeing less than 5 keV nuclear recoils. And indeed, it's consistent with what we've seen before in other bubble chambers, where the Seitz threshold is about half of the true nuclear recoil detection. So they're not exactly the same. But here, if you kind of project out the pink points here, which are the yttrium beryllium neutrons, then they intersect with the background at about 2.5 keV. You can't take this too seriously. It's a kind of an extrapolation, but it is consistent with what we've seen before. And here, just to show that we're doing some simulations to turn this into a real nuclear recoil efficiency. So this is just photoneutron production, propagating those neutrons to the chambers in progress. As far as light detection in noble elements, here's the big one, coincident bubble nucleation and scintillation. So one of the biggest appeals of what we're doing with the liquid noble bubble chambers is that we get spectral information in the scintillation. So in a bubble chamber, like in a Freon bubble chamber or whatever, all you know is that you had energy above the threshold. Other than that, you don't get any energy information. So if it's a nuclear recoil at 1 keV or 20 keV, you can't tell the difference really. And so if you want to really only focus on nuclear recoils very near to your threshold, you need some extra information. Worth saying that in Pico, we can discriminate alphas out. They make a different sound, but not higher energy neutrons, for example. So here with the scintillation channel, we can see some scintillation with our higher energy nuclear recoils and veto those from the signal region as backgrounds. So we demonstrate this with a californium-252 source, comparing just to background events. This chamber was operated kind of in the basement, so mostly on the surface, so it's not a low background environment. Anyway, the red is californium in both of these plots, and the black is the background events. The one on the left is just the rate. So overall, the rate is higher with californium, plotted against how much light you detect. The one on the right is the spectrum, the distribution of the light in terms of the bubbles. So the black, the background, is strongly peaked at thousands of photoelectrons, and there's a little bit down here at 0, 1, 2 photoelectrons. So there's some just low energy neutrons bouncing around the room, of course, but the californium is strongly peaked the other way, where most of the bubbles have no light or a handful of photoelectrons. And then you also see a bump up here where it kind of coincides with the background spectrum. And so if you make a cut here at, say, 500 photoelectrons, then you've eliminated a large portion of the background events out of your californium data set, or eventually out of your WIMP or neutrino data set. So with that scintillation cut on the californium-252 data, we can also start to turn that into a nuclear recoil efficiency analysis. So Daniel Durnford will talk later about this type of analysis, but to turn your data sets in a bubble chamber into an actual efficiency versus like recoil energy, it's not that trivial, but reducing the background helps, and this first californium data set allows us to get a first look at that. And again, we're consistent with the threshold being about 2 times the Seitz threshold. So this is the main kind of plot here. We have most of our californium data is around 1 keV. So 1 keV Seitz threshold, 0.9 to 2 keV really. And you can see that the efficiency does start to turn on immediately at 0.9 keV Seitz threshold and rises. And so you're getting these, maybe 2 times the Seitz threshold, at least under 5 keV nuclear recoils we're detecting. This constraint will improve when we add the photoneutrons into this analysis. So like I said, we're working on that, and then we'll be able to constrain these a little bit better. So I just want to reiterate, in other words, we've demonstrated sensitivity to keV, even maybe sub keV nuclear recoils, while remaining entirely blind to electron recoils at 10⁻⁷ bubbles per gamma interaction level in liquid xenon. Okay, so conclusions, all of what I just said, at about a keV sites threshold, we've confirmed that we're insensitive to gammas in the xenon bubble chamber. We've confirmed that the sites model is still a good predictor of nuclear recoil detection, and we've made use of the scintillation accompanying bubble nucleation events to veto backgrounds, just like we would like to do in a WIMP search in the future. Next step is to incorporate the photoneutron data into that nuclear recoil efficiency analysis, and we're writing a paper on all of this. And we're also building the next generation scintillating bubble chamber. Hopefully you saw Eric Dahl's talk yesterday about the 10 kilogram liquid argon bubble chamber that we're building at Fermilab. Here's a picture of it. That's an exciting new adventure. So thank you, and I'll be happy to take questions about either xenon bubble chamber or the future argon bubble chambers.
Thank you, Matthew, for this nice work. Questions? If not, thank you again, and we will move to the next speaker. Chami? A proposal to use neutron capture as a source of ultra-low energy nuclear recoils in liquid xenon.
Thanks. Could you see my screen?
Yes.
Okay. Hi, everyone. My name is Chami Amarasinghe, and I'm a graduate student at the University of Michigan. Today, I'll be talking about a proposal to use neutron capture in a small detector that we have to measure the NR yields below a keV. And this is some work that we've been doing at Michigan with an undergraduate, Ruben Coronel, Dongcheng Huang, and Maurice authors, and our advisor, Wolfgang Lorenzen. Okay, so the goal is a measurement of the scintillation and ionization yields in liquid xenon below around 0.3 keV. We ran some simulations using the Michigan xenon or the mix detector and the pulse neutron generator. And the principle of generating these recoils is neutron capture, particularly on xenon nuclei, after which the emission of the prompt gamma rays recoil the nucleus, as shown in this cartoon here, so all of these gamma rays have on order MeV energies. There can be several of them emitted, leaving the nucleus with an NR energy of around on the order of 100 eV. So, like I said, several gamma rays could be emitted following the capture, and we consider our signal events these events where all of the gamma rays escape the active volume of the detector without depositing energy. Therefore, the initial interaction site inside the TPC will have a pure NR signature. Now, this plot shows the simulated recoils of neutron interactions in the mixed detector. And I want to bring your focus onto these green lines. The dark green one shows all of the NR deposits due to the neutron capture, and the shaded green region retains only the events where the gammas escape the active volume. So in order for a good amount of the gamma rays to escape the active volume, you require a small TPC. So this is what MIX is. It's a small dual phase liquid xenon TPC that was built some time ago, designed to have a high signal collection according to these G1 and G2 values shown here. This diagram shows a model of the mix detector. So right inside here is the TPC, just labeled here, the drift region. There are 4 top PMTs and one, so the top PMTs are 1-inch PMTs, and there's a larger 3-inch bottom PMT. There is a fair amount of liquid xenon outside the TPC, which we are planning to instrument with silicon photomultipliers in order to instrument it. And shown in this diagram and also included in our simulations is a volume of water intended to moderate neutrons. So we used Baccarat, which is a GENT4-based simulation package developed by Deluxe and LZ collaborations to simulate the passage and interactions of the neutrons in the mix. For the neutron source, we assumed a pulsed beam of 2.45 MeV neutrons as if coming from a pulsed DD source. And they were shot at the detector from outside. And like I said, we've included a 5 centimeter thick water tank to moderate the neutron energies. And these experimental parameters, including the pulse width of the neutron source, the frequency of pulsing, and the thickness of the water moderator thickness, were optimized using results from the simulation. Okay, so the interesting thing that happens when you have a pulse source and a water moderator is it imposes an arrangement of the neutron interactions in time that allows us to separate out the NRs due to captures alone, as opposed to elastic neutron scattering and inelastic neutron scattering. So briefly, in each beam pulse, the water moderator tank serves as a filter to filter the neutrons based on speed. It allows the fast ones to propagate through earlier and the slow ones at a later time. So this is taken advantage of because the neutron capture cross-section scales inversely with the neutron speed. So the capture events will occur much later than the scatters. And as a result, there's a window of time of about 500 microseconds where the only NRs in the TPC will be due to neutron capture. This is kind of illustrated in this plot on the right, where we see the neutron interactions as a function of time of flight since they were emitted. The elastic processes, the elastic neutron scatters shown in this dashed purple line are cut off kind of quickly, after which the only NRs in the system are due to the neutron captures. So the typical timing parameters that we assumed are a neutron pulse width of about 30 microseconds and a pulsing frequency of about 60 hertz. These constraints are given to us when we take into consideration the backgrounds that we expect in the experiment, which we'll get into. But first, quick aside about the neutron pulse width. So in addition to the backgrounds, we also have to consider the total yield of neutron captures that we expect in the detector. So one thing that factors into this is the neutron pulse width. In basic terms, an increase in the neutron pulse width causes the number of signals to increase, as one would expect, until the elastic scatters overlap with the captures, and this decreases our signal window. So this is shown in the plot on top, where as you increase the neutron pulse width, the counts in the signal window kind of go up linearly until it's tapered off because the elastic scatters cut into the signal window at earlier times. And these trends are shown for various different thicknesses of the water tank. Another thing to consider, but it's kind of similar, is the fraction of capture signals that happen after the last elastic scatter, expressed as a fraction of the total number of neutron capture signals. And this metric, due to the same effect of the elastic scatters impinging upon the neutron scatter time, the neutron capture time, this metric also decreases as you increase the neutron pulse width. So these are some hints of constraints we can get of the neutron pulse width just by considering the total amount of captures we expect. The backgrounds, firstly, the low energy ER background was simulated, and at this first estimate, it shows not to be a concern. Around the 0.2 to 0.3 keV NR region. It's it's effectively negligible. And so these are from the same the simulations that we did. A major background, on the other hand, are the single electron backgrounds. So these are typically E-trains following large S2s with more than 100 keV EE energy deposits. And these prove to be a big obstacle for the ionization measurement. We can get around this by using the pulse nature of the neutron source. So the single electron emission timescales are on the order of 10 microseconds, as found by the Lux collaboration in their study of these emissions. And so we have to prevent it from being, this timescale from being longer than the acquisition windows. This effectively constrains our neutron pulsing frequency because we want for the single electron emission to die down before we start our next neutron pulse. So we have not measured this timescale in the mixed detector yet. So we just assume that the single electron emission has a timescale of about 10 or around 10 milliseconds. And this gives us a hard constraint on the maximum neutron pulsing frequency we can have. There are mitigations to this. In addition to using the neutron pulsing, this single electron background rate can be further suppressed by tagging the capture-induced NR signals inside the TPC using the cascade gammas that escape and deposit energy in the skin. And this can be carried out once the mixed skin is instrumented with silicon multiplier tubes. And this cartoon just shows the basic way that one could do this. Another consideration is from ER contamination. So since this is a very gamma-rich environment due to the neutron captures happening, these large ERs often contaminate the capture NRs inside the signal window. There's a trade-off between the number of neutron capture signals that we can have and mitigating the ER contamination. So just for example, if you have a larger water tank, there's going to be more neutron thermalization and there's going to be more captures in the TPC, but there's also going to be more captures on the nuclei outside the TPC, be it the hydrogen in the water or the xenon in the skin, from which the gamma rays can come into and deposit energy in the TPC. So there's a compromise that has to be reached for the water tank sizes and the neutron pulse width. And this plot shows the probability of having a clean signal window for various different water tank thicknesses and as a function of the neutron pulse width. So this provides a harder constraint on the neutron pulse width. Since this proposal is a model-dependent measurement, we require knowledge of the uncertainty of the NR spectrum. So there are a few sources of uncertainty that we've taken into account. Firstly, the imperfect knowledge that we have of the gamma cascades that each isotope emits following neutron capture. And so we use two databases and the deviations between them to quantify this uncertainty. And as of right now, there is very little data about the multiplicity distributions for each isotope following capture. And so we assumed complete ignorance of this, and we basically use the difference between broad multiplicity distributions where each multiplicity is almost equally likely and very narrow ones that are peaked, and quantify the difference between those. And we found that the NR spectrum is kind of robust to all these sources of uncertainty, primarily because the random directions in which the gamma rays are emitted, effectively, these errors are kind of averaged out, and our recoil spectrum is well constrained. Like, we are confident in the recoil spectrum in certain energy ranges that we wish to consider, like from 0.1 to about 0.25 keV. So the experimental setup, I have some pictures shown here. This summer, we have been preparing the mixed detector for these operations. This picture shows a close-up of the TPC. So right here is the big 3-inch bottom PMT, and you have the top 4 PMTs here, and 3 sheets of the grids. And on the right picture, it's just an overview of the entire system, our gas handling system, the cryostat, and the instrumentation panel. Okay, so to summarize, we've performed some neutron transport simulations that indicate a source of NRs below 0.3 keV produced by neutron capture. And these events can be selected and isolated in time with the help of a small TPC, a pulse neutron source, and some kind of moderating material. A simulation-dependent measurement of the NR yields can be carried out if you fit a yield model to the measurements, assuming that the NR energy spectrum is correct. And to quantify this, we've taken into account several uncertainties, including the deviations of the measured gamma cascades in xenon and our ignorance of the multiplicities. There are a few obstacles to performing this experiment, primarily ER contamination and small electron backgrounds. And the ideas to mitigate these are currently being investigated for our setup. And yeah, preparations for this measurement are ongoing. And a write-up of this concept will be appearing on the archive soon. And yeah, these are my references. So this idea of using neutron capture is not entirely new. This has been carried out in germanium in the 70s and has recently been studied further in that medium. As for the neutron capture idea in liquid xenon, there's been some work in Lux by Peter and Matthew explaining this idea, and it's been adapted for a small TPC in DQ Vaughan's thesis here. And these other references are to do with the mix detector, the simulations, and the databases that we use to quantify the uncertainties. Thank you very much, and I'll be happy to answer some questions if there are any.